In 15.2.16.1, we spoke about the concept of the EM spectrum and how EM waves travel at the speed of light. And then we went a little bit further into detail about, you know what? Well, can we find the velocity of those waves? Can we figure out the frequency, the wavelength? And we did a little bit of that in 15.2.16.1. Then in 17.1, we talked about reflection and refraction. Then in 17.2 and 3, we talked about that phenomena called total internal reflection, where it has the critical angle. Then we went into chapter 19, began chapter 19 with the concept of electric charges and what they do to each other. And then after that, we went into 19.2 and 3, where we looked at electric forces that act on one another. So we kind of dabbled a little bit with EM, into more light and the bending of light, and then finally into electricity and the intro to electricity. So this test has multiple topics on it, as you know, that are not necessarily related to each other, right? You picked up on that right now? So 17 and 19 are pretty independent of one another. We're not utilizing stuff from 17 in chapter 19. Now, you had a problem set due today. I can start by taking questions on it. I could also just start by going through formulas first. I'll give you the floor if you want to ask questions first that you have, and then I can go into a couple of things. Try not to get distracted, guys. It's just people on the roof. That's all it is.
I have a question.
Yeah.
It was 52, 55, 58, number 74 about the left sink looking like more shallow or like more deep than another.
What number, Chris?
74.
I think that was one.
I don't think
That's
so.
not on.
Oh,
It was 75 and 77.
It's all right. It's not bad to look at it still, though.
for 15 too?
Yeah, no, for 17.
75.
73,
Oh,
That's
do
what
you
I
mean
meant,
the
that's what I meant,
U,
sorry.
V, A, B, C?
Yeah.
Oh, yeah.
What did I tell you?
You're talking about page 558, number 74?
Number 74, yeah.
Yeah, that was the
558.
UV one.
That says UV light is typically divided into three categories, A, B, and C. They give you different wavelengths, and all they want you to do is find the range of frequencies. So find the largest and smallest wavelength, and use those to find the smallest and largest frequencies.
I looked at, that's what I did. I looked at page 74, or number 74 and 630.
Oh, you're on 630?
I was on the,
And that's optics, I guess? 630? Anyway, okay, does that answer your question, Chris? Yeah. Now, page 630, 74 is all about optics, and we haven't actually done that. That's with like we did the basics of it, but we didn't get into the math behind it and stuff. That's fine. All right, questions. Chapter 15, 16, 1, chapter 17, chapter 19.
Just a quick question. So for like the notation, I know when it's mu c, it's -6. So when it's just c, would it just be the charge itself? Like so, if it's like 0.22, it would just be 0.22.
Absolutely.
Oh, they're gonna play the songs for Spanish.
Okay, those are your prefixes you got to know for your charges. Definitely need to know those two. Those are the two that show up a lot. Now, do you need to know milli in general? Yes. So if I give you something with millicoulombs, milli is 10 to the -3. Okay, so you should know that because you've done things with millimeters this year already. So you should kind of know that concept. But you're not going to get something that says like kilocoulomb or megacoulomb. That'd be a lot of charge. A lot of charge. Okay, now if you're talking about things that are like celestial bodies and maybe like the charge on the ions on the surface of the sun, then it's a little bit different. Okay, but we're looking specifically here on Earth in terms of things that are a bit smaller.
And also with that, isn't like AM KHZ, and then FM is MHZ, and then what are those, like 6 and 3?
Yeah, mega is 10 to the 6, and kilo is 10 to the 3rd. Yep, and that's he's talking about for like frequencies. If I tell you 220 megahertz, that's going to be 220 times 10 to the 6 hertz. And then the other one, 220 kilohertz, that would yield 220 times 10 to the 3rd. Yep. So there's a decent amount of prefixes, I guess, you would know for this test, right? You would know these for chapter 19. I know, guys, just bear with it. You would know these for 15.2.16.1. Okay?
What song is it?
What else? Questions, problem set, homework. Yeah, Bridge, go.
For 19.
I have a question. So, I asked the material and he answered it. I just want to so when you're doing a number line problem, right? And you're determining whether it's going to be positive or negative at the end, repulsive or whatever. So you're looking at the actual charge, not where it is in the number line, right?
Correct.
Okay.
The number line location has nothing to do with attractive or repulsive.
Distance that you're gonna
The number line just gives you the distance for the equation.
Okay.
But if I have a positive here and a negative here, it doesn't matter how far apart they are, it's still considered attractive.
Okay.
Okay? And remember, this is something I want to note because some people have been having trouble with this. I'm going to go to the next slide. You done?
Or the only problem we had, number 72. I just want to go over that.
Oh yeah.
Yeah, can you go back?
Hang on, let me look. Hang on.
Look, in Slater, they had a different.
Yeah, oh, this is the one this morning we talked. Slater's wrong. Slater's wrong. What's the answer?
It's
7.9.
I got 7.9.
Yeah, you're good. Slater's wrong for that one. I told you, remember, Slater's not always right.
Just checking.
Yeah, that's fine. Hey, this example, Slater is absolutely not right. So if you got 7.9, Lauren?
Yeah,
M?
7.9 to the right.
7.9 to the right. Okay? Yeah. Correct. Guys, if your distances are given in centimeters, they need to be in meters. So this problem does give centimeters here. You should always be fair game for that.
It's to the right because it's
The pull to the right was more than the pull to the left in this problem. Centimeters 2, because centi is 100. 100 is 2 zeros. Until you remember. Something to note, if I have this, let's look at this arrangement. Okay? And I ask you to find the net force acting on this particle here. When I draw this particle, I assume that this particle can move and the others are fixed. So, this particle will get pulled to the right from this guy right here. Call this 1, 2, and 3. It would get pulled to the right from number 2. So we would say that there's a force acting on particle 1 from particle 2, and it's pulling it to the right. But if particle 2 weren't there, and only particle 3 were there, particle 3 would cause this guy to get pushed this way. So we would say that there's a force on particle 1 from particle 3. So remember, the particle of interest is the one that can move. And the one that can move, we draw the forces that would cause it to move as a result of the other 2 particles. Now, I give you an example in your homework of 2 particles, but does it need to be 2? Of 3 particles. Does it need to be 3? It could be 4. It could be 5 particles. And then you just have a couple different extra arrows, right? So if I had an additional one, let me just show you. Let's say I had a negative over here. Let's call this particle 4. Well, what would particle 4 do to particle 1? Particle 4 would pull particle 1 to the right. So what I would do is this. I would draw an additional force extending from this arrow. And this one is F12. This one is F14. You see what I'm getting at here? So charges 2 and 4 both pull this to the right. So I'm drawing 2 collinear arrows, vectors drawn to the right. Particle 3 pushes this guy to the left, and that's the 1 arrow on the left. So any problem could have 7 forces, 12 forces. Now, am I going to do that on a test? Probably not, because it would just take forever, right? So you could expect 3 particles at the minimum. Could I ask you 4? Maybe. Maybe I include a 4th as like a little bonus or a little extra piece. But I'm just putting the idea out there that 3 is not the limit, right? We all see that? 3 is not the limit in these problems.
So could particle 2 push particle 4 away so it wouldn't have an impact?
So again, particles 2, 3, and 4 interact with each other. But what am I asking you about for this problem? Particle 1. Remember, all the problems, all the charges interact with all the other ones. But it's a matter of what are you asking about. So on the test, I will ask you about one of the particles, not all 3. Because your homework or your problem set, if I recall, you had to find the net force on the first particle, the net force on the second particle, the net force on the third particle. That's just a lot of redundancies. So because it's a test, and because tests are timed, and because tomorrow is a BEX, be examined, It's only 40-minute periods. So I'm definitely not going to have you find the force on every single particle. It will be find the force on one of them, and I'll specify which one. Clear? Okay. It's a good question from 19. Yeah?
For the law that has, I think it's for like Schnell's law. Is that
Yeah.
what it's called?
Snell.
Snell. What?
It could be Schnell if you want to make it Schnell. That works.
I thought it was Schnell.
Same. I was like,
I guess it could. Maybe it's Schnell. Who knows? Good.
When there's a higher index of diffraction, is the index of, I mean the.
Let's write this up because I know what you're talking about. Snell's law. Let's start with. And what we'll notice here is this. And Gigi's talking about the value of n and when n changes, what ends up happening and stuff. So there's a couple ways we can interpret this. If n goes up compared to the original n, so let's say this is 1.2 and now this is 1.5. If n goes up, angle's got to go down. The only way for this to work is the angle goes down. And you'll learn more about this in your trig in fourth quarter of math that you haven't started yet, but you'll see that the sine function, as theta goes up, the sine function goes up. So if n goes up, then the theta value has to go down. So say this is like 42 degrees. This answer has to be something less than 42 degrees. Is that clear what I'm saying? So if you go from a lower n to a higher n, the angle has to go from a higher angle to a lower angle.
So like impulse.
Yeah, like impulse. Yeah, like impulse. Higher force, less time because it equals a constant delta P. Good analogy there. Very much like impulse. So let's draw a diagram of that. Let's say that this n value is called Ni and this is called Nr. And I tell you that this angle is 27 degrees. This is a great multiple choice type question, by the way. Like a great multiple choice question here. So I'm going to just put a line to separate these problems. So I'm looking below the red line here for a separate problem. So if I tell you the following, if I tell you that Ni is greater than Nr, what can you conclude about theta r? If Ni is more than Nr, Alex,
Then the angle of refraction is greater than the index angle.
why?
Because if you have a higher index of refraction, then you need to have a smaller angle.
Because they are?
Formulas.
How are they related?
Indirectly related.
Yeah, they're pretty much indirectly related. So take a look what Alex is saying. If Ni is a bigger number, and this is a certain angle, some value, and then Nr goes down compared to that, the refracted angle needs to be greater. So when I look at this, it's going to bend away from the normal. So this angle might now be like, I don't know, 52 degrees, whatever. Some value greater than 27. It's a great multiple choice problem where you don't need any math. You don't need any math. I'm not going to give you n's. I'll say, if Ni is bigger than Nr, which of the following multiple choice could be the value of theta r? So you would answer with any angle as a multiple choice that is bigger than 27. So you're not going to be able to calculate this angle, 52. We don't know it. But we know that Ni is more than Nr, so we know that theta r has to be more than theta I. So if you have four choices, they'll probably be, ready? I'll give one choice of like 0. 0. Another choice less than 27. Not going to be that one because we know it's got to be greater. Another choice will be exactly 27, which means it wouldn't bend at all. If it doesn't bend at all, it means that these are equal to each other, right? That was the Pyrex demo I did for you that day, where I poured the vegetable oil and the Pyrex disappeared. It was because these were the same. So the bending of light didn't occur, and that's why you didn't see the Pyrex. So 27 isn't an answer either, but an answer more than 27 would be your answer. Okay, I'm not saying you have to calculate it on a multiple choice, but you have to be able to theorize the type of answer you'd get relative to the initial incident angle you were given in the problem.
So how do you know when it's bending away from the normal or towards the normal?
you can know from this, if you want to think about it, with Snell's law. You could say, well, if the n value goes from a higher to a lower, theta goes from a lower to a higher. They're just inversely related. So if this goes from a lower to a higher, this goes from a higher to a lower. And a lower means it would bend toward the normal. That's one way of thinking about it. You could also think about what n actually means. What's the value for n for air?
1.
1. Every other value is what?
Greater than 1.
Greater than 1. And isn't air the fastest moving medium, we've said? So everything else is going to do what? When it enters from air into something else, it's going to slow down. It's going to slow down. And when that happens, when the wave fronts slow down, we're going from a lower n to a higher n. So low to high means this goes from high to low. Do you see the indirect relationship that exists between n and thetas? Okay? So it depends on which way you want to remember it. You can just memorize in general what's happening, or you can use Snell's law to remind you, ooh, what's happening here? This is bigger, this is smaller, so this needs to be smaller when this is bigger, which is why this answer was bigger than what we started with.
Okay, so basically when it's going from a faster medium to a slower medium, it's going to bend away.
Well, no, this case is going slower and faster. We're starting with a big N, which is slow, to a lower N, right? Take a look at the statement. You're starting with a bigger N, and you're ending with a lower N. A bigger N means slower, because what's the fastest moving medium again? And that's a 1, isn't it? And 1 is the lowest N. The lowest N makes it faster. And we're going from, again, a big N to a lower N. So it's going to go from slower to faster. So when it speeds up, it bends away from the normal, actually. It bends away from the normal. That's why you have total internal reflection occurring with like the fish tank example. Because it's going from water, which is slow, into air. Into air, which is fast. So that'll bend away from the normal. And if it happens enough, so call this water, and call that air if you want. Okay? Water to air. If I keep, take a look at the diagram. If I keep increasing my incident angle, and let's say now I make my incident angle for the next laser ray, let's say like 40 degrees. If I increase that angle enough, it'll make this keep bending further and further away from the normal. So the next one might look like that. So it'll make that angle even bigger. That makes that like say 75 degrees. So this is where the critical angle idea came from. If I continue to increase theta I and make this larger and larger and larger, this angle will get larger and larger until it bends all the way back into the substance. Again, if I look where I'm pointing, if I make this larger and larger and larger, the refracted angle keeps getting larger, and anything more than 90 means it bends back all the way to here. So that's what will happen if this laser comes in at a low enough angle, it'll bend back into the substance, and we call that total internal reflection. Okay, it's really refraction that's happening, but because it looks like reflection, we call it that. I gave the example of fiber optic cables. I gave the example of a light in a pool in the summertime at night, why the pool seems to glow. And then we tried to do the example of the fish tank, and it was mediocre of a demo. Okay, it was mediocre. Alex?
So if you give us a problem and you say that you don't give us the internal angle, but you say that there's total
Internal reflection occurring.
yeah, then you just make that 90 degrees.
You can make theta r 90 degrees, yes. But you could also, Alex, when you're told that total internal reflection occurs, you can go right to this formula. Oops, let me use a different color. That's not good. Critical angle equals inverse sine of, in this case, let me just make sure it's right. What is our formula? It's going to be the smaller one on top, which is air, so NR, over the larger one on the bottom, which is NI. Okay? So, Alex, you could use that to find, remember, what is the critical angle? It's the angle incident that causes total internal reflection. So in this case, the critical angle would be, take a look, the angle between the normal and the incident ray. This green ray right here. That's the critical angle that we're looking for. The critical angle, remember, is the incident angle that causes total internal reflection. All right, good. Chapter 17 questions. Good questions. What else? What other questions? Want to go through some formulas in general here? So if I'm looking, I don't know my formula sheet. I want to look at exactly the formulas I give you in this section. If I'm looking at my formula sheet, in chapter 15, 2:16:1, the only formula that we're really going to utilize is this right here. But in 15:2:16:1, since they're EM waves, we could set velocity equal to the speed of light. And that'll help us for those problems. That's the only formula from 15:2:16:1 I think that we utilized. Hold on, I'm just pulling up your formula sheet to make sure I have every formula listed here. Is this you guys singing? Or some people singing?
This is the other section.
So I'm opening your formula sheet just to take a look. All right, here we go. So,
You watch it.
yeah, all right, that's the only formula then. Well, I guess technically I could ask you for, if you can find the frequency, I could ask you for the period, right? And the period is simply 1 over the frequency. So technically, if you were to use that above formula and solve it for frequency, you could then find the period also because they're related to each other. Does that make sense where the frequency could be used? Okay. Now in chapter 17, and then we'll go to chapter 19. In chapter 17, we've got this first formula right here. This allows us to find the n value. If I don't give you a table, but I tell you, ooh, there's a new medium, it's unknown, you don't know if it's glass or diamond or air or water, but there's a new medium, and suddenly the velocity of the EM waves drops from the speed of light, and then it hits this new surface, and it drops to, say, 2 times 10 to the 6. Well, then I would go ahead and plug 2 times 10 to the 6 in here, plug the speed of light in here, and then I can get the n value for that new medium. So remember that V is the speed of the EM wave in the new medium. V is the speed of the EM wave in the new medium. C is just the speed of light in a vacuum. And that's a constant, and that's on your formula sheet. Then Snell's law, I just wrote already. I'll write it one more time, though. Here it is. I'm going to make everything in degrees on this test. I'm not going to have you do things with radians, just because I'm not going to have you test it on radians right now. So I'll tell you now that you should have your calculator in degree mode. In degree mode. And then third is that critical angle I just mentioned. SAT is mostly in degrees, but I guess the subject test, if you take the SAT 2 for math, some of that is in radians, I think.
That'd be so hard.
It's not hard, I promise you. Wait till you're done with the fourth quarter of math. Radians are going to be like second nature. It's just another unit, like inches to feet.
We just did the 2 pi equals.
Oh, nice. So you derived the whole thing in the beginning?
Yeah, it's like exactly the same thing that we learned in physics.
Yeah, but it was like
Counterclockwise.
Counterclockwise, positive,
Oh
clockwise.
yeah,
negative.
on our SAT on Saturday there's something with
There was
physics.
something that had to do with physics, and I saw it, and I was like, "Oh, this is easy."
No way. What topic was it?
It was like
Wait, we can't talk about it. Hold on. Chapter 19. Chapter 19. Now, something to point out. Please listen. Listen. Something to point out. I ask you about the magnitude of the electric force always. So when on your formula sheet, this is how it's given. And I'm not going to put absolute value bars on a formula sheet because I will use the word magnitude. I will say, find the magnitude of the electric force. And then I'll say, is it attractive or repulsive? So you need to use the nature of the setup to know whether it's attractive or repulsive. But when you plug in for Q1 and Q2, even if one of the charges is negative, you always plug in positive for Q1 and Q2. Again, you always plug in a positive for Q1 and Q2, even if one of them is indeed negative. Again, the negative positive only tells you whether the force is attractive or repulsive. So on your test tomorrow, please remember to do this if you're forgetting. Okay, remember to put that absolute value bar around the electric force. R is the gap between the particles. Q1 and Q2 are the charges themselves. K is your constant, Coulomb's constant. What formula did we say this is analogous to?
To the gravitational.
Good. And that's not a formula that I'm going to have you use on the test, but I could maybe ask questions about that concept. Okay, but the gravitational formula, this is not from chapter 19. This is not from chapter 19, but I'm going to put it below so you can see it. Okay, those are analogous to each other. They're analogous. We should understand that concept. All right, that's it for formulas for chapter 19. That's it. Yeah, that's it for formulas here. And your constants are on the bottom. So at this point, I'm just going to ask you what you want to go over, really. What would you like to do? What kind of a problem would you like to go through?
Go over some conceptual stuff.
Sure. Sure. So, conceptual stuff. Let's see. 15.2, 16.1, EM spectrum. So, EM spectrum, you should know the concept that as frequency goes up, wavelength goes down. And that was shown on that chart. If you remember, the radio waves were at the top, and they had a large wavelength, but they had a very small frequency. And then at the other end, we had gamma radiation, which had a very, very small wavelength and a very high frequency. So that relationship that exists, you should be able to identify at least some applications. That'll probably show up more of multiple choice or short answer. I'd probably lend it to multiple choice, but I haven't made the test yet. It's tomorrow, but I got to make it tonight at some point. So it'll probably be multiple choice for you guys. But the concept of, like, if I say something like heat vision in goggles or heat vision goggles, you should know that that's infrared. Infrared involves heat, a heat signature that a body gives off. If it's something like ultraviolet, you should know that that's just above the violet. Ultraviolet, just above violet. Infrared, just below red. Again, don't memorize every single application, but know the ones that we kind of talked about in class and have ideas of them. What else conceptually from that section? We talked about dispersion of light. Dispersion of light is taking white light and bending it in a way that you see, a rainbow. And what we see in the sky is simply the bending of light at a specific frequency, and that frequency corresponds to the blue wavelength. Red, yellow, green, blue, violet, indigo, all of them have their own wavelengths and their own frequencies. So when we're referring to these parts or these types of colors, what we're seeing is a specific frequency of light. Frequency of it. What else? Let me think. What else?
Oh, like how black is like being observed.
Yeah, white light is the reflection of all colors coming off of a surface. Black light is the surface absorbing all of those colors. So nothing is being reflected off of it. Green light is only seeing green reflected off the surface and every other color being absorbed. Red, green, and blue being our cone receptors in the eye. And those being the three colors of light when we're talking about waves.
Red, green, blue.
Red, green, blue. Those are the three, yeah. And then where does yellow come from? It comes from a combination of blue and green, right? Blue and green, I think. It's not like an art class, right? It's not like an art class the same as the color wheel. Remember, it's slightly different from art class where it's like yellow. What is art?
It's yellow.
Yellow, blue, red. So replace yellow with green, really, for light.
What do you have? I'm kidding.
think that's it conceptually for that. Chapter 17, conceptual stuff for chapter 17. Bending of light. Bending of light. Where could it be used? It could be used with lenses. We talked about convex and concave lenses. Concave lenses diverge. Convex lenses converge. Now, we can have combinations of them as well, but we didn't get into lenses in this course. That's what, where's Birch? That's what you looked at for that example. That you looked at the wrong part. That had to do with using lenses to look at the trajectory of the light and the angle, looking at what are called focal lengths. We didn't get into any of that kind of stuff. By the way, for those subject tests that are thinking of subject tests for physics, that is a topic that's on there, optics, and that's a chapter that we didn't really go into a lot. I think it's chapter 16 in your book. Yeah. Chapter 16 involves all that stuff. What else? What else? Theoretical stuff. Oh, we talked about this. We talked about this a couple times. This is a diagram from page 603 if it's not clear and you want to look at it afterward. This is a person's eye. And a person sees an object that's in the water. And this is the actual shape of the object in the water. But what the person sees is physically a bending of that object. Okay, so this is what the person actually sees. And this is the actual location. We gave examples of this a couple times. I showed an image of like a slab of glass with the person's finger and the person's hand. So like this is a stick figure of the person's hand. Let's say here's all their fingers coming off of there. And then they take one finger, and there's the thumb. This finger suddenly gets shifted over, and then it comes out the other end. I can't draw a hand, sorry guys. But that's my image of it. Yeah, it's in the notes. I actually showed this image in the notes itself. And this concept I want you to recognize is that here's what's happening. Here's what's happening. And you recall I did this in class. Here's a window pane. Air, glass, air. As the EM wave strikes the surface of the glass itself, it gets bent away from toward the normal a little bit. Let me draw a normal here. It gets bent. I'm going to zoom in a tiny bit on this too. It gets bent, in this case, towards the normal. So it starts to look kind of like that. But then when it goes out back into air, it bends away from the normal again. So although the yellow vector doesn't look parallel to the red vector, the two red vectors themselves are parallel. And they're just shifted. What should the trajectory of the red line look like? It should look like this. Okay, but these guys are really quite parallel to each other. Let me draw that nice and better there. That's what it would look like. So the light or the EM wave should travel in this trajectory in black, the dotted black line here. But instead it bends toward the normal, hits the new interface, bends back away from the normal. So when it comes out, these two red vectors are actually parallel to each other. That's why that finger shows a staggered look. It's staggered when it's in the glass, and then when it comes back out, it's still next to where it started. Okay, this is what's happening when you look out the window. You just don't see it. It's not a shift that occurs enough that we see things staggered. That's apparent light. A prism is literally doing this, right? We talked about what a prism is. A prism disperses light, very much like raindrops or mini prisms. When there's enough moisture in the air after it rains, you see a rainbow usually at the end, because the rain or the water molecules in the air act as little tiny prisms, and they disperse the light that travels through them. I mean, I don't really need to show this, but there's your example of a prism. Light hitting it and breaking into all the colors of the spectrum.
That's total internal.
By the way, I went to Cooper Hewitt the other day, the museum. I've mentioned this a couple times down the road. Really cool. Exhibits right now are on color and light.
Okay, let's go.
Like if you want to today, and you have not you have nothing to do, but if you really have an hour to kill, it's free for students. You can go there for free. Just show a student ID. You might have to sign up online first before you go, but I think if you just show up with a student ID, they'll let you in. Under 18 and under is what it is. Anyway, the whole exhibit on light and color talked about how actually, indigo isn't really a color wavelength, but one of our founders of color, I forget who it is that really did a lot of work in this area, related sound to light. And if those that are in music know, you think about a scale. How many notes are there on a scale? Is it 8? It's not 7?
There's two.
One that repeats. But we assume that's the next scale. So 7 notes to an octave, 7 wavelengths or 7 types of colors. So I can't remember who it is, but he was a like a Renaissance man who dabbled in music and physics and math and all these different areas. And when studying this, used 7 colors to represent the different 7 levels of sound in an octave. That's where it actually comes from. So, fun fact. Anyway. So, applications of this, we talked about fiber optics. So a cable like this, there's an EM wave. It's traveling through the cable. It hits this wall at such a very large, like take a look at the incident angle here, please. There's theta I right there. It hits the cable at such a large theta I that it causes, instead of this object to pass through, it bends back so much that it bends back into the medium. And the refracted angle is this, again, it's not really passing through. The refracted angle is this right here. So theta R becomes more than 90 degrees, causing it to bounce back into the cable. And then this continues its process throughout. It hits there, hits there, hits there, hits there. And I showed this as a quick demo with the water that was spurting out of the 2-liter bottle of Coke. Steve showed it, remember? The water was going like this, and the light ray continued to travel through the water even when it was curved. That's an example of fiber optics, an application of it. We also talked about lenses in Chapter 17 and how they can be used for corrective lenses. So if somebody has nearsightedness, if you recall, here's the eye. The light ray enters the eye, and it focuses too near to where it started. So it's too near. So instead, we want those rays to diverge a little bit in the beginning. So we put what we think of as it's not exactly like this, obviously, you know that. But we put a lens there that causes the light rays to diverge a little bit, so that they diverge a little bit, and as a result, because they're diverging to start, they converge a little bit later. And then they focus on the retina. So nearsightedness, nearsighted is corrected with a diverging lens. A diverging lens. Again, nearsighted, it focuses too near to where it started to focus. Too near. Farsightedness is the opposite. Farsightedness, the rays focus too far away. And we want to converge them sooner. So instead of using a diverging lens like we do for nearsighted, we use a converging lens for farsighted. I could give you a problem like that and talk about the angles and have you use refraction to do it and just show a diagram. So you could expect something like that, maybe a math problem that shows a person's eye and shows the rays focusing, and I have you calculate the angle using Snell's law. And it's just an application of it, and you would just use Snell's law the same way you would do for any other interface. I think that's all I want to cover in 17. A lot of 17.3 we do not cover. That's why I kind of combine those. You'll notice, like focal length, object distance, image distance, magnification, all that stuff is not covered. I call it 17.2 and 3, but technically the stuff with the human eye is from 17.4. But whatever, it's no big deal. All right. Chapter 19, theoretical stuff. Theoretical stuff from chapter 19. First, if something has a charge, what does it mean? If something has a charge, what does it mean? Alex?
That there's either more protons and electrons or other way around.
Okay, I like it. Now, how can we have more protons or electrons? How? Physically.
Do transfers.
What are transferred?
Any charge, anything that's charged, electrons and protons.
Only electrons. Remember, if something, you asked about theoretical, right? You guys said conceptual questions. If something is positively charged, it does not have an abundance of protons suddenly. It has a deficit of electrons. So a rod that has been charged using wool and rubbing the rod itself might suddenly have a lot of a negative charge. It means that that rod gained electrons. But if that rod was rubbed against wool, the wool cloth lost a bunch of electrons to give it to the rod. So the wool cloth would have a positive charge on it the entire time. Okay, would have a positive charge on it the entire time. There's a demo. Maybe I can upload it to Drive and show you the video of it. Steve did it, but in the other class the other day, not in here. So unfortunately, it's going to be tough for you guys to see it. Here we go. Let me upload this to Drive and I can share it. There's a video. I'll try to share it with you guys, demoing this. Study hard, please. Any hard copies of problem sets? Any hard copies?